Is the sounds okay, guys? Make sure.
Yes.
Just want to make sure I'm not muted again.
It's all good. Your sound is clear.
All right, all right. We are in the thing again. How many people is this here? Yep. So, um, it is a weird thing because a lot of people, when they introduce other people into the field, is that they try to go from the neurons route. They try to what is it? Convince you that it is inspired by neuron, which most likely it is. I don't know the history or anything. And this will just tell you, look at this. You have all of this weird circle. They connect like this. Each of this has a number. Let's just get along with it. And all of this number follow a certain equation. You have the input multiply with that number plus the second input multiply with the second number. Hold on, I cannot type that. Right? Multiply with the second number and so on and so forth. So each of those input has its corresponding connection, the weights thing, Wn. And this, they tell you throw it into an activation function. But which is fine. A lot of the videos, everything, documentation, everything is all about this. But what if we started slightly differently? We want to see why is it this way. I already sort of went through this last time already, some time ago. Today I found a dataset, a very popular one called iris species. It contains information such as sepal length, width, petal length, and width in centimeter about a type of flower called iris. And there are three different types of them in this dataset, and those are, how do I see them? Setosa, versicolor, and virginica. So this is from Kaggle. You can check it out if you get your account working. If not, download it. I already downloaded it and I will import it in the notebook we have here. It is here. Last time we used pandas to go through our data, and we're gonna use matplotlib. You can see the text right from there, just like that. Okay. Um, let's list something first. Make sure I don't mispronounce anything. So we have three different files. We can use the CSV one. So pandas dot, if you remember, you do that, give it the file name. So iris.csv. This thing gives you a data frame again. So let's call it df for now. And then we can inspect that data frame. You could just say df, and that would be a lot of them. 150 row, 6 column. Hold on, where is it? Yeah, let's just put head. List only the top 5. So we have all of this information, and they give you species at the end. So given sepal length, width, and petal length and width, what is the types of flower? That is our task today. You could use regression. You could use some basic machine learning stuff, and that should be enough to perform this task. But the goal today is to try understand Perceptron in a high level way, like not just about math. Even though we're gonna do practically try to write our own Perceptron here, try to train it, make sure that we understand the whole flow. We still want to make sure that we don't just imagine neural network as a bunch of nodes and all of those. So if you take a look at this neural network, every time it's just a bunch of this thing, right? So what does that even mean? Why does it connect to all of them all at once? Does it even make sense at all to connect them all at once like that? Is it fast or whatever? So those are the questions we're going to try to answer. But I'm not organized to be honest. So I'm trying to get along with it. So we see our data frame. The data set look like that. It has all of this information. Take the column species, value count. It will count the unique number of value. So iris, setosa, there's 50 of them. Versicolor 50, this is 50. So this data set is evenly distributed. That's the term. Basically, they give you an even number of each classes, so that when you train, you don't have to worry that this class is more than the other class, and you don't have to worry that your model will focus too much or memorize too much on one class and doesn't understand the other. In the case where each of this class might be not properly distributed, you have to do some normalization. I don't know how to do that exactly. There is a term called EA analysis or something. That's not right. I forgot the term. Don't worry about it. All right. So we see our database, data set. We have 4 input, trying to predict 1 output, 3 different class. So let's go to this. We have 4 different inputs. Let me know if you have any question, by the way. For different input, our job is try to predict 3 different things. So those are Setosa, pronounce it wrong I guess, and Virginica. So we need a way to extract something about all of this information. We have sepal length and width. So if we think about it, the length and width, the sepal, by the way, let's check out what is all of this even mean. Iris flower. We sort of cheat a little by try to go through all of this flower and see what there are. So iris is sort of this flower. They're mostly blue. There are also other color. I'm not an expert. I'm just Google it up and see that here. Check out the type. So these are the exact data set we have. Setosa look like this, versicolor, virginica. But I don't know what's the difference exactly. Maybe the color is different. But the problem is our dataset doesn't have any of those color information. We only have all of this dimension related, right? So maybe try to find a different thing that is good enough for us to differentiate. This one should be fine. Let's see. So if you can see, the petal is distinct, sepal is distinct. Now the sepal look very similar to each other, so we don't really care, except that this one is a bit smaller than the other, right? The petal length of this one is a bit larger. The virginica is the largest one. Setosa is the smallest, and this one seems to be a medium size. It's not large, it's not the same as this, but it's not too small either. So those are the things that we just observe, right? As a human, it is so easy to look at this and try to find the different things. And we are able to find the thing that can use to differentiate all 3 of them at the same time without having any of them collide. So if we know that the pedaling is big, it must be this one. It's not gonna be this one. So we know that this is a medium. It's not a big one or a small one. A neural network, on the other hand, it might just see 2 things. And I did try to go through this last night and try to explain it to nobody. And then it turns out it's very hard to think of something as a medium value. We can find something between 0 to 1 as a small to large, right? The smallest to largest, but how do we think of something in the medium? Sure, you can put the value in between. So if the pedal length, if the pedal size is somewhere in between, that is medium, but how do you extract those? So those are a bunch of other questions that we have to get into the math, but we don't want to do it today. We just want to look at this and try to think of what does the neural network is thinking. Not just the perceptron, because perceptron alone doesn't make any difference. So we're going to try to think all of this as a network in a whole. Any questions so far? Hello?
Nope. Nope. All good.
Everything's good so far.
It's good so far. All right.
Yeah.
Let's cook. Let's get going. So what we just did is that we look at this. We know it is a pedal. And instead of looking at this two value, length and width, we sort of understand that it is a size immediately. So from this two thing, right, we sort of extract a bunch of other information in between as a human so that we can determine each of this by ourselves. So what we just did is that we sort of extract whether they are medium or large or small, right? So what if we do that here? Is pedal small or not? Medium. We don't really care about the symbol for now because it seems to be the same for us, but we're gonna use it anyway later on. Or large. The reason I split them into small, medium, or large is because if we use just one, it's gonna be something like a pedal size. But the way the math work around here is that it's not gonna be good to differentiate at all. How do you put? Well, don't worry about it. I'm getting ahead of myself. So let's just take this three, and we take a look at this two input, right? Pedal length and width. That means somehow we can use this information to determine whether they are small or not. Both of them, use both of them. And whether they are medium or not. Same thing here for large or not. We have this sort of in-between layers of abstraction. All of this input is too low level. You have all of this value, length, and width. We don't really care. What we want to know is whether they're small, medium, or large, right? Now, after we get this, we don't know whether it is gonna work. This is like a super simplified version of neural network, and it doesn't really mean it's gonna be like this. But let's say it technically or hypothetically, it can get all of this value for us. That means now we should be able to use them for all of these three flowers, right? So Setosa need to be a small pedal. So if this is true, this connection sort of we do some math with it, we don't know yet, and should trigger Setosa to be a 1, right? So we assume that this value is between something, after that we between a range, and then after that we got a 0 and 1 value, and after that we also got a 0 and 1 value. We just want to know whether they are true or not, right? Same thing for versicolor, as it seemed to be a medium size. So if this is a 1, we do some math with it so that the versicolor also must be 1. For the large, Virginica. But we don't just connect it like this, we also connect the other one to each other. So if it is small, we know if it is large, it must not be small. But in the case where the model in the front here doesn't work so well, where it is small and large at the same time, we don't want it to, we want to make sure that it's not small and large at the same time. So if it is small, we want to sort of ignore them. That's why it is red, and I'll explain why it is red and what does it mean exactly. and also at the same time medium. So we only want to know if it is large, but if it is also medium and small and a few other information later, we want to ignore them. Those values should drag them down and try to make this Vijayanagara as a 0 rather than a 1. Does that make sense? We do the same thing for this and this. So that's why you see all of these things are connected densely. It's called a dense layer. Everything connect to everything else all at once. Sometimes you don't have to. Let's say for some reason we should be able to extract another information called, let's say, if it is yellow or not. Sometimes you just want to ignore them, right? You don't want to take them into the account. To ignore, we don't connect them, but we connect them anyway, but using a different value later. That's not well prepared, but yeah, something like that. Okay. Pause a bit, drink some water. Any question? This is quiet. I don't like this.
No question.
No question.
All good.
All good. Okay. Really, no question. I thought this is weird stuff. All right, let's get going.
Oh, hello.
No. Yeah.
Is it okay if I ask a question? Okay.
Yes. Come on. What is happening?
So I kind
I
of
think
missed this.
we kind of. Sorry.
Oh,
Oh,
Go ahead.
going right now. Okay. So I kind of got lost with when you started pointing the is pedal small to like the versicolor stuff.
yeah.
Could you try explaining that again?
Oh, this part.
Yes, that part.
Yeah. So as a human, we already sort of we don't use this information immediately, right? Even though they are available to us, we can use a measure, try to measure the size and get all of this value. We don't do that. We take a
Uh-huh.
look at it. We sort of jump straight to this layer by determine whether they're small, medium, or large, right? And after that, after we
Mhm.
know this, we can use this information, which can be any 0 or 1 because they are Boolean value, to determine whether something of any of this is a true or false. Does that make sense? So
Yeah.
for something to be a setosa, it must be small. It must not be medium, and it must not be large.
Large, yeah.
That is our expression, right?
Yeah.
But what if we want something a bit more complicated rather than just a Boolean, a binary expression like this? Well, usually I'm just gonna put it out here and we can think about it later. Something that is a not, we subtract them, or in other words, you multiply it by -1. So this is essentially -1, multiply with it, and then we add for all of them. Karina, you was saying something or something?
No. I wanted to mention that we kind of uh went through this. I think last semester you showed this in
Yeah,
class.
that
So
was so
that's why.
much. Yeah,
Yeah, that's why we had no question.
okay. It was so much more prepared than this. Sort of jump around. Yeah. So, by the way, those are it sound well, but then I try to prove each of those statement that I wrote down here, for example, -1 and all this, and it's not real. It just some assumption, high level thinking. It doesn't make sense. But yeah, it does sounds good as another perspective into the field itself, rather than think of a bunch of number. We can try to derive why it looked like that in the first place. Eventually, we got to the point of the same where people at the end where we have the same equation as other people, right? So that's what we're trying to do here. So we multiply negative to the connection that we don't want it to it is influencing the red connection, but we don't want it to be true. So if it is small, it must be small for this. So in the ideal case for setosa, small must be 1. Everything else must be 0, right? So let's say this thing is not 0. Let's say it is 1. That now mean small is 1, medium is also 0, large is 1. And if you multiply -1, it is now negative. This is plus. So 1 plus 0 minus 1, it is 0. But in the ideal case, this should be 0, which should now be 1. So in the ideal case, the value that we sum up should equal to something like larger or equal to 1, right? So that's what's happening. That's why the connection is red. We put the negative value here. So what I'm trying to get here is that connection negative, all of this, where is the equation? We deleted it. Remember the thing we wrote down from other people Perceptron. So W1, W2. All of this add together, right? And if the input is true or false, let's say it is between 0 and 1 for now. It doesn't need to be discrete value. It can be a continuous between 0 and 1. We add them all together, right? And in the ideal case, where the model has learned that it is true to be setosa, it must surpass a certain value, something like 1, but we don't know exactly what that value is. So each of these weight sort of tune itself in a way that if it realized that the other feature, the medium for example, need to be ignored or need to be go the other way around, like try to prevent it from being true, it will be negative value. So negative value sort of amplified each of this value in the negative way that it drag your total value down. So that's what's happening. So if it is positive, it will contribute to the whole thing and it will influence your total to a certain value. So all of this will be a total value, right? And anything that is negative will drag the total down. And all of this addition just gonna give, I don't know why it's keep pasting a bunch of number in there. Total is that. The negative value will drag it down, but all this is just a number. So if you want to know whether something is true or not, you take this total and you apply an activation function. This is where activation function comes in. So you ask whether it is larger than something or not. And we don't usually know what that something is, so we give it a value, right? But we don't put it on this side. So if you throw it on this side, it is now negative, larger than 0. The reason we do this is because we want to make sure we can extract this activation function into a function that is generic, that we can use for any expression. So now instead of calling this, put it into the activation function. Now we call negative b here, but it doesn't really matter because if the model learn that b need to be negative, it will give it the negative value by itself. So we sort of let it learn. Yeah, that's another thing that is important. We have two things about neural network is that all of this, we sort of, as a human, we cheated a little. We look at this flower and we know there are a bunch of things we want to extract. And we know what are the features we want to use to get all of this value. And what features to get all of this value at the same time. But neural network, it doesn't know that. And to show you, to make everyone think as a neural network is what if we have another flower, another iris, sort of. but we don't know what exactly it looked like, right? That means, how should I even connect it to any of this? What is the connection going to be? If it is it positive or negative? We don't know. So what we're going to do is we pretend not to know and we give it some value. That is where weights come from. Right? That's why we have W1, 2, and 3. Because we don't know, we're just going to give it some random value and we let it learn. So I'm just going to write it down. It's cringe, but let it learn, brother. That's one thing. We don't know which one to connect to, so we connect to all of them anyway. So connect to everything all at once. Okay? So two important things. We don't know exactly what features we need, so we connect them to every features we have. And all of this feature in between doesn't even really matter to be something or not at all. It can be something that we don't even know. That's why we call it a node H1, the hidden layer H2, something like that. H3, H4, and so on. So all of this doesn't need to be something. We just gonna let it learn, and whatever will work best for the network, we just gonna let it be. Same thing for this. Now, same thing happen on this layer to determine something, to determine if H1 is true or not, or between 0 and 1 or some other value. We don't exactly know what H1 is. That means we don't even know what connection we need to make, right? So if we don't know, let's just connect it to everything and let it learn. We finally get to the point and I'm so happy right now. But yeah, we don't know the connection, so connect it to everything. That's why neural network does this. That's why you see they are densely connected. But later on, when we work with image, there is a inherent problem with this, and I'm trying to do some visualization for to explain it later when we have a chance. But right now, this is worked fine. And in terms of efficiency, this is not slow at all. It's very fast, and the reason is we're gonna talk about it in a bit. So, anyone get this idea? If you don't know the connection, just connect it to everything, and then give it some random value, a variable that the model can learn. And for those who was in Andrew class last time, I explained how we let it learn, right? We just notch it a little and try to match it with the output and propagate it backward and update all of these weights and biases, right? So that is why weights is there, why the activation function is there. The activation function, this is the step function if it is larger than 0. But the problem is, what if you already see this thing is not larger than 0. It is 1, but we sort of throw 1 to this side, and that is bias. So this is where bias come from. So we sort of derive in a way. It was everywhere all at once, but yeah. So instead of put bias here, we usually put it along with each of this, plus bias at the end, and put into the activation at the after that. And this gives us the node value. Any question? To summarize this.
Yeah, I have a question.
Oh yeah.
Why is it plus bias and not minus bias?
Okay, that is a very good question. So let's say the network. So we don't know what bias is, right? We let it learn, right? And
Yeah.
what if it is need to be negative? Well, bias will it's gonna be negative no matter what. So if the model learned that bias need to be negative, it's just gonna give it value, negative value. And plus with negative value, it's just going to be negative, right? -1,
Okay, yeah, I got it.
right? So we use plus. It's just like a general we generalize it so that we don't have to worry or whether I want to give it negative or plus for each of this. The sign for each of this number is embedded directly with this, and that is sort of nice and neat because we don't have to worry about the sign at all. And then we use the same equation for all of our output. So each of this, now we stop using this. We do the same thing for all of this with a different sets of weights and bias value. The activation function for each of them too. Right? So for each of this types of flower, they will have its own sets of connection to the input in the previous layer. So this is a hidden layer. So writing down W1 and 2 and 3 is not really accurate. What we should write is W1, 2, 1, 3, and so on. And bias is 1 for this setosa. And this is 2, 1, 2, 2, 2, 3, bias 2, and so on. So that is just another detail about this. So we go through, not go through, for each of this, we do the same thing. We calculate it by accumulate or combine all of the connections and input, plus some bias and apply some activation function. Now, this activation function can be a different one. It can be the sigmoid or other function that we need. Usually we use ReLU. ReLU is that if it is larger than, it is x, if x is larger than 0, otherwise it is 0. So this is a bit better than step function because if it is a true value, we don't just know it is true, we can also know how true it is at the same time. That's sort of my interpretation of the ReLU function. We have sigmoid that gives you the value between 0 and 1, just like the step function, but this time instead of a discrete cut like this, it is sort of more smoother between 0 and 1. So let's say this is 1. This value is going to be something like this. And this is good for the output like what we have here, because probability need to be between 0 and 1, even though we still need to normalize it later. So we don't want it to be like 2 down here and this is 1. We want to be able to convert it into percentage. That's why we can convert it into 0 and 1. So in this case, we apply sigmoid on this layer, ReLU on this layer, and nothing because this is input. And the reason we use ReLU is because it's fast, simple, fast, and it's good enough. It doesn't need to be anything fancy. But in the output, we actually need to use something that does make sense. We don't just use some random thing, right? So those are the thing. So, we spent too much time on this. Any questions so far? I thought I had something to talk about. I forgot already. All right, let's ignore that and go back to the notebook. Oh yeah, let's summarize it real quick. So our perceptron was that way. It's because what we just talked about. We want to sort of use a combination of them to extract some certain information in this node over here. So each of those has a W, has a weight, and each of this node has a bias value, a B. The reason bias is there, again, I did not express this enough, is because the activation function has a threshold at 0 no matter what. So ReLU is always at 0, step function 0, sigmoid 0. But if the threshold need to be different. The model will learn the bias value for that to shift the threshold left and right so that it can activate the output value a bit differently. So we have more freedom to activate them at a different threshold rather than at 0 all the time. And if we don't have the bias, it's going to be a problem because everything activates at 0 and it's really hard to differentiate all of this value from each other. Sometimes all of this will be activated at the same time, even though the weights and everything is good. It is impossible to differentiate them without the bias. So now that we have bias, it's still a bit hard, but it is decent. It should help us a bit. So each of this input multiply, input multiply, input multiply, add some bias activation function. So the hidden layer is the activation function input weight plus input weight plus input weight. All of these are different value, by the way, but I'm too lazy to write them down. Just like that, right? This is for Perceptron. That's just the thing we Andrew talked about last week. But we're gonna go through a dense layer. It is the same thing. It's just Perceptron with multiple. It's just multiple Perceptron for this layer. And each of these connections are different. They're not the same at all. Now the reason we go through this is because we can use some math operation to make it fast. So even though they're all connected, everything connected to everything else, there is some GPU. We can use GPU to perform the operation so fast that we don't have to worry about speed at all. And that will not work by doing this. We don't just do it like this. Let's just get to this for now. I will explain what that means. So we sort of have all of this input, length and width again, and we will try to make our own perceptron right here. And just I'm going back again. I'm so sorry. The layer we're gonna have to simplify thing because the math is gonna be very tough. We're just gonna have one layer. So this is our perceptron. We're gonna do this, connect to this directly, and we'll see if there is any problem with that, right? So first of all, let's write something for setosa. Write some expression that we learn about here to determine whether it's setosa or not. So if we go to the node again, back and forth, let's create some variable. So we know we have weights, so I'm just gonna say weight 1, weight 2, weight 3, weight 4, because there's 4 input and a bias. All of this should be random. So I'm gonna use a torch. .random 1, and I will explain what this means. Let's see. That is slow. Oh, it shut down. We went away for too long. Oh boy, that's gonna be tough.
Just to clarify, right? The activation function that you mentioned earlier, that results to either 0 or 1, right?
It can be different. So let's go through all the
Okay.
activation function. ReLU. This is ReLU. If it is
Uh-huh.
if the input is less than 0, it is 0. Otherwise, it is X. It is the input itself, which means it could be anything
Hmm.
above
Oh,
0.
okay. So it's not just 0 and 1 then.
This is not 0 and 1, right? Sigmoid is 0 and 1. Oh, what is this? Why sigmoid? Yeah,
What's up with your research? Oh, sigmoid cone. Okay, that's why.
yeah. So sigmoid look like that. It
Uh-huh.
it clip everything between 0 and 1. It is for probability. Not exactly probability, because probability is that all of this value, each of them must be 0 and 1, but also the sum of all of them must be add up to 1, right? So we normalize it and we get that. The other one is tangent, tan h. This is between -1 and 1. So the same as sigmoid, but it leaked down all the way to -1. I don't know what the use of this exactly. I don't know. Yeah, those are the decent one that we
Uh,
use a lot. Each of this
for
activation,
activation.
sorry,
Oh, go on, go on.
yeah, each of this is for a single node only. So you add them up, you add the bias and put it into the activation function, right? But
Uh-huh.
we have a different types of activation function called softmax, which is for probability. This is the one. So it is sigmoid with normalization. And this apply to all of the node at the same time. So if you have all of this node, right, and it is not normalized, you see between 5 and some of them is 0, close to 0, they go through all of them and divide it by the total sum for each of them, so that the highest one still is the highest and the smallest one is still the smallest, but when you add them all up you got 1. That's how probability is, right? It is just some rule that you have to add them up into 1. So you have to put
Yeah.
softmax on the layer, not just a node, the layer, to get that.
Okay, okay.
Yeah, if you have anything, just ask.
More questions?
Yeah,
Okay, okay. Let's as I think I need to clarification as well for this one. Hold on.
yeah.
So in this part, could you go to the field row?
Which one?
The total ones, right?
Oh, here.
These are these hold on. How do I rephrase this question? These are neurons, right? Or no?
Yeah, but we avoid
Oh,
talking
okay.
about neuron, to be honest.
Not for now. Okay, okay, okay.
Yeah. The only thing I want
Anything?
everyone. Sorry.
Go on, go on, go on.
No, no. Go ahead, please. Go ahead. Go ahead.
Okay, okay, okay. Because like, hold on. I'm still rephrasing my question. You can go on.
Okay. Yeah, the only thing I want everyone to get here is that one way to think about this is extracting features as a bunch of combination, and the way we do that is all of this equation. But
Mm-hmm.
the reason they all connected, you see, they all connected with the activation function is, and all of those, and the bias and all of those is because we don't know exactly what we want to connect it to, and we don't know what is the value for the connection. So we sort of do this, connect everything and let it learn. And
Oh, okay, okay.
yeah, and I set this up so that when we got to image processing for neural network, there is a different architecture that we need to use it to for the neural network to work with image. This will work fine if you have an image. It's not fine at all if the image is too large, but it's still gonna work, but it's very terrible. So we have to think about a different way of doing so and why we need them. It's just a bunch of why, right? We ask them and then try to figure out what we can do about it. Is Karina back? Is the break over?
I am
Yeah.
back.
Okay, she's
Did you
back.
go?
Oh, there we
Sorry.
go.
Yeah. What was the question, Alfred?
Oh no, it's about like the total part. So like the inputs and stuff.
Yeah.
Um, hold on. Actually, never mind, never mind. I can't rephrase the question.
Okay, don't worry
Never
about it.
mind.
Yeah, so we didn't went far, we just talked. So we're gonna try to create our own perceptron, and in order to do that, we're gonna create a bunch of variables like we talked about, a bunch of weights and bias. And you see torch.ran. One is that I want a random value with a single number with the one dimension. So this is what it's look like. So if I run torch.ran and give it 1, it will generate me a number. Oh no, not again. Shut down again. Oh, it's back. A single tensor. So this is what we call tensor. And the reason is because we're going to do some back propagation later, and we don't want to do it by hand. So this is what it's look like, right? If you want something fancy, like a list of random number, give it a 5. You will get 5. You want 5 by 4 by 3, you will get those list of numbers. So it's pretty neat for with PyTorch. We could even generate an image. So 5 by 5, and just for fun, we're gonna do some plotting. Image show. I don't know if it's gonna work. Okay, thank God. It is working. So 5 by 5 is some random image. So that's that. Let's not get into it. So we generate a bunch of random number for each of this. Now to calculate setosa is we're gonna use each of those. Now what are the input? We don't know the input yet. So let's try to get the input. So the input is each of this. Let's go through data frame. Our data frame 0, the first value in the data frame. That is surprisingly slow. I forgot we had to do ilog. That is hard to look at. Let's do dot values instead. So this is our data frame, the first value. So these are the input, and these are the target. So we could do this. We could dot value and get the first one, and get the value here, which is the first 1, 2, 2, 3, 4, maybe. Let's see. No, 5. So we get all of this value, right? And each of those must multiply with each of this weights. So technically we don't do this. We do this and multiply with weight plus that, and so on. So you see, each of these are input, multiply with weight, input, weight, input, weight. And then in order to go through all of the data, we could go for loop in the range of our data frame. And then instead of 0, we can put I in there to get each row. But this is tedious. It's a goofy way to go through this. Now the reason we use tensor in the first place, because this library allow us to go through all of this number all at once. Not exactly all at once, but we don't have to do a for loop like this. So let's not do that. What I'm gonna do is data frame, and I'm gonna get the what is it? Sepal length. Can I copy it? Why is it so hard to copy this? Oh, not again. Oh. You know, let's just write it. So that is our first input. So those are each of the input. I'm just comment one for now and see what the other one look like. And it's basically a list of number dot values. So it's an array of number, right? What we can do, if we do this, we multiply it with the weight. And even though weight is a single number and this is an array, NumPy or PyTorch know exactly what it needs to do. It's basically take this and it multiply for each of this value directly. So it take W1 and go through each of this number and multiply it for you. And that should give us another array. Okay, never mind. Tensor and NumPy is not the same. So what we have to do is to convert this into a torch.tensor. Now we have two tensor array. Multiply with a single tensor value and it will go through each of this and multiply it for you. Right? So we're going to do the same thing for all of them. Hopefully the auto-completion is working. Yes. And then we add them all up. And then we add the bias at the end. Oh, bias might not work. Let's just do this for now. So we got an array. Let's call this Z. There is no bias in this Z, but we're just gonna do it anyway. Right, I'm just gonna do dot shape to see what's the dimension. So it says an array of 150. Now for each of this, we want to add bias into it. Wait, that is kind of weird though. I think I might get something wrong here. No, actually I'm not. It's fine. So adding bias is not going to work because Z is 150 and bias is only 1. B.shape, let's see. 150 and 1. And by the way, this might be confusing. 150 is not number of nodes. It is number of data points. So you have 150 inputs. Not all of this. Our input is only 4, but we have 150 of them. Does that make sense? So for each of those 150, we want to add bias to each of those. So that means we have to somehow make this bias into 152, but with the same number for all of them. That is some weird thing about tensor, is that you have to do some math thing just to make it work for now, because we don't want it to go through individual number one by one, so we have to do a lot of goofy things. So let's try to figure that out. I have bias with the shapes of 1. How can I duplicate them into 150? That is our question. I honestly have no idea. Let's try to figure out. Permute. Just gonna change the shape. Maybe ask the AI. Duplicate. B into. Oh, that's cool. You can call repeat. Let's see if it is actually working. Before we assign bet, let's run it. Okay, you can see now it's not 1 anymore, it's become 150. But this is just going to return something. It doesn't update the B itself. That's why we have to put it back into B. Now our bias is 150 of them. The same thing. The same 150. So Z plus bias. And then we put this into the activation function. So I'm going to put plus bias here. And then we're going to apply some activation function onto this. So let's put Z for now. dot shape. That's not right. We have a 150 by 150. Do we have to repeat this? I'm so sorry, guys. We have to go through this. Okay, never mind. we don't have to repeat the b. So even though b is just a single number, it's just gonna go through each of those 150 and add b into it for you. Does that make sense? Now we're gonna create a activation function. We could create ourselves a sigmoid if we want, and it's just gonna look like this as the AI suggested. But PyTorch already have an activation function for you, and it is in the functional module. So import torch.nn.functional as f. So we import this as a capital F and we can use it. So setosa is essentially z, and f dot sigmoid on that. It will go through each number and apply sigmoid for each of those for you. I forgot to run this. It's deprecated, but it's fine. So now we have it. We have a setosa, and this is not just a single of input from our dataset. It is all of them. We go through 150 all at once. Dot shape. Right? Now we don't have a target. We don't have a oh, we do have a target, the class. Where is it? It's gone. The species. So we can compare our output here with those. But before we do that, we want to do this for all of the types of flowers. So it's not just setosa. With each of this, we want each weight sets and biases for the other flowers too. And I'm sort of exhausted right now and cannot explain it properly. Let's go through this. So you see we have each of this, weights and biases. And each of this, we can do the same thing as we did right now, right? Multiply and then apply activation function and get each of this. And then we have to create another set for this second flower, another set for this flower. But in math, we have a way of doing this a bit easier. So instead of creating a bunch of this individually, we can create a matrix of them. So all of this can be organized into a matrix of weights. So our input is 4 of them. Oh, hold on. Our input, instead of think about it as a single number individually, we can group them into a vector. This is where the actual important part comes in. So we're gonna ignore what we just did, and we're gonna go through our input. So the first value is actually for different input. Let's get all of those first. And I will remove species. This will give me all the input. Is equal to that. And if I took a look at the shape, there is 150 value, and each of those is a vector of 4 value. A vector essentially mean a list of number or arrays of number. And the reason we, instead of thinking of it as a single input one at a time, we group them into a vector like this. So if I go through, let's put this into a value, into an array. I can take the first one, and this is my vector, right? So instead of what we did last time, where we go through each of this, individually multiplied weight, individually multiplied weight, and so on, we take all of this at the same time, and we're going to do something about it to get our list of output. Rather than get a single output, we're going to get the whole 3 output at the same time. So that's what we can do. But in order to do that, we need a way to organize our weights. So we just organize our input into a list of vector. Now our weight, we can organize them into a matrix. A matrix is basically a list of lists. So it's a 2D array, right? So for each of this, we're going to organize it in this form. So a matrix that is a 3 by 4 matrix. The reason is because the output is 3, the input is 4. It is backward, by the way. So row is 3, columns is 4, because the first row is corresponding to all of the input for this, all of the weight for this node, right? So I have a W1, 1. So this one, hold on, stick with me. So 1, W1, 2, 3, and 4. Any question? What we have here is all of this input, and we go through rows. So each of this row will contain a list of all of these weights over here, the connection that comes into it. So 1, 2, 3, 4. So 1, 1, 1, 2, 1, 3, 1, 4. That's what it's look like. And we have 3 rows, 3 by 4. So the second one is 2, 2, and so on. So I'm just going to change it to avoid any confusion. This one is 3, 3, 3, and 3. Any questions so far? That's our matrix.
Yep. Okay.
Sorry?
No question so far.
No
Yeah.
question so far. Okay. Yeah, so that's our matrix, right? The only confusion so far, or at least for me when I was learning about it, is that it's sort of backward. The row is the number of output, the columns is the number of input. And the reason we do this is there because a fancy math operation that we can use to do what we just did for each of this, but it will work for all of them at the same time. Well, we're gonna go through each number individually, but it will go through them. If we use GPU, it will go through all of them at the same time. So 3 by 4, let's remove this from here. Now remember, our input is also a vector, right? So it's gonna be a 4 vector. So 1, 2, 3, 4. This is not clean. I hate this. Right? And I put my input on this side because there is an operation called the matrix multiplication. I'm not sure if you heard of it, and you don't have to really get into the linear algebra or anything. This is very simple. So what you have to do, you matrix multiply your weight matrix with your input vector, and when you do that, the way you do matrix multiplication is you do this. You take your input. This is how I like to do it. You take it, put it on top, you rotate it like this, and you go through each of this. So if you look at it, right, the one that align, you multiply them. So you multiply each of this next to the one that is aligned, and you add them together, and that would give us some value for this row over here. So we will write that down, and you do the same thing for the next row and next row. I'll do it again, but this time we will try to... Damn, my OCD is serious. What's happening? So the output is with 3 value. The metric multiplication give you a vector of 3, the shape of 3. So when I take this, I multiply and add them, I get this single row over here. I do the same thing here, I got this one. Do same thing here, I got the third one. So, and if we take a look at it, what we want, that is not proper. Let's write that down real quick. I'm sorry that we have to go through this. So what we want is W11 multiplied with the input 1 plus W12 multiplied with input 2 plus W13 multiplied with that thing. Input 3, W14 and input 4. And this is only for the first row, and it is corresponding to this single node over here, right? And if you do it the same way for all of them, I'm not gonna write it, it's gonna bore you to hell. So it is the exact same thing we want it to be. So what we have is that this thing, this value over here is equal to this input multiply the connection it's connecting to, this input multiply with the connection, this input, the connection, this input, the connection. And it works so well, and it gives you the exact same thing you want as right here. So that's the output. We can simplify the output even further into, let's call it H1, H2, and H3. Right? So that's metric multiplication. Your input is a vector, your weights is a matrix, and you do metric multiplication, and the way that metric multiplication work is nice enough to give us what we want, and then we got the linear combination. This is linear combination that we have. Now to add bias, all you have to do is to put your bias into a vector, just like the input, but the vector for the bias is only the shape of 3, right? Because there are 3 different nodes. That means each of them has a bias on its own, right? Bias 1, 2, and 3. That means the bias would have the same shape as the output. So bias 1, B1, B2, and B3. And if you add them, the vector addition is very simple. You add the corresponding value. So if you think about it, it's the exact same thing we want too, right? So H1 plus B1, and that would give us the same thing, but with the addition. I should not call it H, call it Z or something. But you got the idea. So to summarize, for this single layer, is that your input is now a vector. Let's call it X with hats on top. And your weight is a matrix. So we call it capital W because it is one-dimensional higher than the vector. And your bias is also a vector, so bias with a hat on top. We don't need hat, but you know, hat is cool. Everyone love to have a hat. But after that, to use this is we take your weights. No, hat is only for vector. You metric multiply with your input vector, and then you add your bias vector. All of this you can apply the activation function and then you would get your output vector or hidden layer vector as you want it to be. And even though it looks simplified, this is not simplified. It is the exactly the equation we want that we use. And metric multiplication is cool because it's not just work like this, but it's also very efficient on GPU. Especially it was for gaming, because a lot of this relies on metric multiplication in gaming. So they developed GPU for that specifically, but then we realized GPU can be used for deep learning. That's why we want to use each of these online editor, especially Kaggle. They give you free GPU. So when you got to training, you want to utilize them as much as possible. And it's not going to work out of the box, so you have to do some setup a bit, but that is another thing, right? So the first thing about what we just did is to simplify our life, make it nicer. The second thing is GPU, and that's it. So I don't think we go through this is gonna be tough. So let's just go through it. Go through shape again. So even though our input is a vector with the shapes of 4, we have a batch of them. So 150 of 4. And that's another thing. Even though we already sort of simplified a way to calculate this instead of going through one by one, we do it for all of the input at the same time already. In deep learning, we want to go even further by do it on a sets of batch all at the same time. So that's why all of these are 150 input at the same time. But just to make sure we understand this first, we're gonna get the first input. So the first input is with the shapes of 4, right? Now how do I create a matrix, a weight matrix? So I'm gonna call it weight is equal to torch.random. Ran n, I'm not sure what n is stand for. You could just do this, but do it anyway. So we want a matrix of the size of 3 by 4, just like what we talked about, right? And a bias is with the random of 3. It's already give me that. Very nice. Just call this one more time, b.shape. Make sure we get the exact same thing. So our matrix is 3 by 4 and the bias is 3. Now the input is 4. That means we could do the matrix multiplication here. Weight, and in PyTorch you could use this symbol directly. It's matrix multiplication. Or we could call torch.matmul on the weight, I think, and then the input. Must be a tensor, not okay. We have to convert our input into a numpy, into a tensor. So I'm gonna convert it up here. So torch.tensor. Surround it. Oh boy, not again. It need float 32. It doesn't have as type. That is funny. Okay, I convert all of this value 150 by 4 to a tensor with the types of float 32. That is just another thing that I encounter a lot. Now we create the weights and biases, and then we do a metric multiplication for a single input. And as you can see, you get the output with the size of 3, right? And if your output is big, it's hard to read, just put dot shape, you get 3. So this is a size of 3. That means I could now safely add it with the bias, and should give me something too. So I'm gonna put this into a z for now. Z.shape. Same thing, 3. Doesn't change anything. Now I could apply the activation function straight onto this. So z is equal to f dot sigmoid on z, and I can z dot shape. Doesn't make any sense. It doesn't make any difference. It's the same thing, right? But what we just did is a single layer, a dense layer from scratch. Not exactly from scratch, we use a lot of tool, but at least we understand what we just went through, right? We group this into a matrix, this into a vector, and we got this. And then we do this operation, and bada bing bada boom, we got it. But now, this is only for a single input. Can we do it for all of the input? Well, let's try it. I think, okay, it doesn't make sense. So you see, the metric 1 and metric 2 doesn't have the same size. You see, 3 by 4 multiplied with 1 and 50, it will not work. That's because we cannot multiply a vector of 150 by 4. It only take a 4 vector, right? So, but we do this on a batch. So in Torch, we have a batch metric multiplication, BMM. I hope that this will work. Batch 1 must be a 3D tensor. Okay, so this, it need another dimension into it. Unsqueeze something in there. Okay, never mind. Let's work this out real quick. Weight.shape 3 by 4. What if I do squeeze? No, unsqueeze. Okay. I got that. The second one is 100 by 4. 150 by 4. Actually, if you go to the whiteboard real quick, this metric multiplication is not only going to work with a single vector for the second one, it can also work for matrix to matrix. So I'm just going to try it out. So if you have a matrix of 3 by 4, the only thing it need to have is that whatever row of the second one need to match with the exact same thing as the column of the first one. Right, so it doesn't matter how long this is. It can be 150 just like what we have, right? And we can call the exact same metric multiplication. It doesn't need to be a batch. So if you have this is the exact same thing as before, but this time we use 150. But the problem is our input is not in this shape. It was 150 by 4. So it's the other way around. Right, so what we have to do is to flip this around. And now we got this thing. And now we can do metric multiplication. And just to visualize that, it's pretty simple. So after we convert everything, we should now get this. And then when you flip it, that's why it need to match, because when you flip it, you can see 4 is the same thing. So you boom, 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 boom for one row and for one column, and then you do for the second one in this row, in this matrix, and so on for each 150. So after that, you would get an output of 3 by 150. 3 row and 150 columns, because we have 3 here and 150 here. So that's how metric multiplication work. This thing must match, and the output is the size of this multiplied with this. So that's another detail. So we just talked about it. What we want to do is to flip our data set into, instead of, let's say, x.shape, instead of 150 by 4, is we want it to be 4 by 150. So in Torch we have a permute function that we can flip the dimension. So initially it is dimension 0 and dimension 1. What we can do is I want the dimension 1 to be the first one, dimension 0 later. So hopefully that will work. Permute, that's funny. Now we got 4 by 150, right? That means I could put back into x or use it directly. So put it here, we permute it. Instead of using that, we just use normal matmul and remove the unsqueeze. Okay, rerun this real quick. We update it, that's why it's changed. Okay, it's still not. 3 by 4. Wait, what was the size of the input? We permute it. It's 4 by that. Oh, the bias. Okay, let's ignore bias for now. So we multiply, cannot speak anymore. Multiply this. Now we got a output of 3 with the 150 columns, right? So how do we add this with bias? So we take a look at the thing. The output is 3 by this, and our bias is only 3. How do we add this? It's not gonna add each of this for you, I think. That's why it gives us the error. So if I try z plus bias, yeah, must match the size. So what we can do is to make our bias the same shape as our input, just like before we used the repeat thing, or maybe a reshape might be better. A view 3 by 150. So just to make sure we understand what this means, instead of a single bias with the, okay, that's not right. Should I do this? Still not right. Shape of 3, and I want 150 of them. Okay, so what we can do is dot unsqueeze another dimension into this, the second dimension. Now we have 3 by 1, and let's just use this for now and see if it works. Okay, it does work, but what is the exact output? Three by 150. Okay, it worked. So it just need to match the number of dimension. It doesn't need to match the 150. So because this is a vector, it has only 3, the shape of 3, right? So using unsqueeze, give it another dimension. Even though it is 1, it has now matched the number of dimension rather than the shape, exact shape. It doesn't need to match it. It only need to match the number of dimension. So it will go through each of this 150 and add each one of those for you. So this is what we have here. So, but we could even simplify this even further by initialize our bias in the correct form initially. So instead of just 3, we're going to put it 3 by 1 initially, right? Now we should be able to get a metric of 3 by 4 and a bias of 3 by 1. And then after we metric multiply, can add bias immediately to it. And that should help us, should make it work. Yes, 3 by 150. And then we can apply sigmoid or any other function. Relu, could just call relu, just like that. And that would work. But that is only for word propagation. We sort of run out of time. We have a bit of time left. But yeah, so we have weights, right? We just did the forward, what we talked about Matrix multiply plus bias and a activation function to give us the output Z. Not Z, let's call it O. Okay. And O is the shapes of a bunch of them. 3 by 150. This is not 150 by 3. Still, the shape is still weird. We could permute it back if we want to, but we'll see if we need to or not later. So now there's 150 by 3. Does that make sense? Any questions so far? I know I sort of fumble in between. Should have prepared better. But yeah,
No questions for
no
now.
question.
Yeah.
Okay. So that is forward propagation. That is how a neural network works. Not a neural network, a dense layer work. In PyTorch and everything, they help you. You don't even need to do this, to be honest. What you could do is every time you want a dense layer, what we just have is a dense layer, right? So what we can do is create a variable, let's call it layer 1, and we use torch.nn. Let's import it. I'm gonna go to the top, torch.nn as nn, so that we don't have to type that every time. And now we can say nn.linear, so they have a layer for you, linear, and give it the input shape, which is 3 by 4. So this is different from the matrix. Our matrix is, hold on, no, not 3 by 4, 4 by 3, sorry. It's different from our input matrix. The matrix has to be flipped. So what we did here is we create a layers, and this layer is an object. It's not just a function. It is an object that contain weights and bias automatically. So if I say layer 1, we should be able to see something in there. It has in features of 4, output features of 3. I could say maybe dot parameter, I guess. That should give me something. Man, I hate this so much. Give me something. Okay, doesn't matter. I think we can say dot weights. Something like that. So all the weights and bias is already in this object, the layer. And every time you multiply it, every time you call it, so the way you call this is layer 1 dot forward and give it the input, and it will work for your input. It doesn't matter what is the size. Well, let's see if it actually works. I don't want to make any claim. Okay, it's working. It is working. The output with the shapes of 150 by 3. So you see it's already converted your input for you to the output for you too. So instead of 3 by 150, it's 150 by 3 immediately, right? So it works for a list of input at the same time, and it is too good, because if you give it a single input, it might not. Oh, it worked. Never mind. Yeah, but sometimes there's some case that uh, it you need to give it a bunch of things at the same time. If you don't, it's not gonna work. But in this case, for some reason, it worked. So we're gonna take it for that. We don't have to worry. All right. So you can call forward, or you don't have to. Just put it like just a function directly, and that is your output. So your output is equal to this, just like that. 2 lines of code to write what we just went through. And I like to go through this from scratch just like this to see why they are. But I do like some advice. If you think this is terrible way of going through it, please let me know. Next time we can go through something a bit more practical later. Does that make sense? So instead of 4 by 3, we're going to create a layers in between, just like what we have before, but we don't care what those layers have to deal with. We're just going to create a layers and let the model learn. So let's make it with the 5 neurons in the second layer. So our input is 4. It will split out another vectors of 5, and then the second layer, it will take the layers of 5, right, a vector of 5, and split out the output of 3. And in between this, we want to do some activation function. Now we don't know exactly what the feature is gonna be. Like we don't know what the model gonna learn. So we're just gonna use some arbitrary activation function that is work fine, like ReLU. So in between, I'm gonna use a ReLU1 for now, and create another object of ReLU. And then for the output, I'm gonna use let's say softmax. I'm not sure if softmax gonna work. We might need dimension, because it is a batch of them. It doesn't work on, it's only work on a single vector, but if there's a batch, you have to tell it which dimension you want the softmax to work on. Let's just use sigmoid for now, so that we don't get confused. Okay, so those are the setup. And in practice, we don't do this. This is weird. You have to create it outside like this. You have to create a proper class and so on. But another way though, I wonder, you can use this nn.sequential, and you can put your layer in here directly, just like this. So instead of declaring a bunch of variable, you do this. Bing bang boom. This is not a layer anymore, even though it is. You can call it a model. So a model is a sequence of layers, but it works the same way. So you can call, let's run this real quick, model.forward on your input, and that is your output. Let's put the shape. We don't want to look at that. Okay, it worked, right? So that is another way of doing your neural network. You can scale this up very easily, but there's a different way that we can do this, but I don't want to get into that yet. So we haven't split our data set at all, and I don't want to get into that. That's going to take a bit of time, but we're just going to use our data set like this immediately. So our model is this. Now we can forward it like this, and this would give us a prediction. And for those who remember, a flow of neural network is we gonna get the prediction, and we're gonna try to calculate the target, the error, the loss value for each of these predictions. So let's get some target up and running real quick. So our target data frame, and I'm gonna get the species. We're short on times here. So species is a bunch of text. So we want to put it into a category, just like before, cat.codes. Okay, it doesn't work. It doesn't have... Hold on. What if I do this? So what I'm trying to do here is to get a list of target in the forms of number rather than a bunch of text. Okay, now we get that. We put value into an array, a list of target, right? So this target is 0, 1, and 2. So this is what we call a class target. It's not a probability vector. So what we want, when we get the output, our output is in the forms of a 3 vector, right? A vector of 3 dimension. So we want to compare them with the target, but our target is telling us the class directly. So it tells whether it is class 0, class 1, or 2, whether it is need to be this one or this one or this one. But what we want is, we don't want this number. What we want is another vector that tell us what is the probability distribution need to be. What that means is that if it is a versicolor, for example, the versicolor class is 1, the rest is 0. This is what we call a one-hot encoding, because it is one hot. That doesn't make sense, but it is one hot encoding, right? So if the flower, I cannot speak. What we have to do, what's happening? What we're doing here is we assign each of this row of your vector into a specific class. So this may be a versicolor, this may be a setosa, and this is a virginica or something, right? So, and if the class need to be a virginica, the virginica must be 1 and the rest is 0. That's how you do it, a one-hot encoding. So for now, we have the class in the forms of number directly. But what we can do, let's convert this into a vector first, into a tensor. Torch.tensor. And the type need to be a long rather than a float. So let's run that. Okay, we have a tensor, and we can call something like a one hot, I think. Torch.oneHot. Hopefully that will work. Does not work. So let's search up PyTorch one hot. Okay, the function name is different. So one hot. Still not gonna work. I think it's in the functional. Yeah, it is in the functional. So instead of torch, we call f.oneHot. So now you get all of those, and it's automatically understand which class it is in based on the number. So if it is 0, it go through the first one, 1 go through the second, 2 is the third one, right? We can say put this into a target variable. Is that? And target.shape should give us something to understand. On 150 of them, and each of them is 3 vectors, so it's the same shape as our output. So the reason we do this, we're just going to go through this quickly, is that the prediction should be the same shape too. Prediction.shape, same thing. So we could implement our own mean square error, right? So prediction, I don't know which one minus which, so let's just do this. Prediction minus target, and that should give us the same shape. And then for each of those, we want to square them up. So hopefully this will go through each of them and square each of them up. Dot shape again. Same thing. Dot mean. Essentially divided by the largest value, or the number of possible targets. So divided by 150. So this is the mean square error. That is slow. I think we did something wrong. Stopping notebook. That's weird. Come on, we're almost there. Start mean for now. That's how we do the mean square error. Not how we do it. This is terrible. We don't usually do it like this. We use the function that they give us. So PyTorch pred is not defined. You have to run it again. Mean square error. By the way, mean square loss or mean square error is not for classification. The problem we're just doing, we're doing right now is a classification problem. We're trying to classify which types of iris flower it is, right? So another function we usually use is the log loss function. The easy one is the cross entropy loss. And the confusion about this function, you don't need to know the implementation, but the confusion is that it doesn't take a one-hot encoding. What it takes is the exact same thing before the one-hot encoding, the thing that the class vector or the whatever those are. So instead of applying one-hot, all we need to do is to just keep it that way, 150 of them, and each of them is a number corresponding to which class it is, and we can call the the cross entropy directly. So instead of using the mean square, we have our target and prediction. I'm gonna create a loss function real quick. So alongside the model, we're gonna create a loss function, and it is equal to nn.cross entropy loss, right? So create that function, get some prediction, call the loss function on target and prediction. And the reason you do this is because cross entropy will convert your thing into a one-hot encoding for you, or that's what I assume it does. Otherwise, it doesn't need to know one-hot encoding. It doesn't need to do that. Now this will give us a loss value, and we can see what is the loss of our current model. 1, which is not good or not bad either. It is bad. So another thing about cross entropy loss for classification problem is that you don't have to do anything about your output. You don't have to put sigma softmax or anything. Just leave it as it be. I think it take in a something called logit, just a list of a number, and it will try to do softmax for you and everything for you. Yeah, it do softmax for you, so don't worry about it. So whatever model you have here, run the prediction, get the loss, and this your loss is a single number, right? And you can see there's something called grad function here. This essentially means you could call backward. Once you call the backward, it will propagate throughout the function that you just did. So from here to here to here, and go through each of this layer. And for each of those layers, when it's encounter your parameter, which is weights and bias, it will take the partial derivative with respect to that for you, the thing we talked about last time, and essentially telling it which way to go to optimize the value. So after we call backward, we can use another thing called optimizer. So we can create a optimizer, and in torch.optim, we're going to use a stochastic gradient descent. This is basically update your weight. So if your weight is like this, we can take the old one minus some learning rate, multiply with the gradient. And yeah, after you do the backward, each of your weights and bias will have the variable called .grad. So if you do .grad, you get the exact partial derivative you want. So in case you want to do something fancy, you could do this too. But yeah, so stochastic gradient descent look like this, just like that. Learning rate multiplied with that, and this is learning rate, 0.1. And we put model parameter in here so that the optimizer know exactly what are the parameter it need to optimize. So it will go through all the weights and bias and get the gradient value, and then it will update it. But it's not going to update it here. This is just an object that we create. The machine is offline again. I don't know what's happening. What we can do, after you call the backward, you have to clean up the... Hold on. We have to clean it up before the backward. So optimizer .0 grad first. You have to clean up all the gradient so that the back propagation can can give it the new value. if that makes sense. Now, after you clean it up, you call the backward, you can call optimizer.step. Try the backward through graph a second time. Don't worry about it. Run it again. So this is usually the training loop. You get a prediction, right? Call the loss function, empty out the gradient for each of the parameter, call the backward, call the step on the optimizer. So you have all of this, and then this is the step. And usually we don't call it individually like this. We put it into a for loop. This is where we use for loop. But this for loop is not for every single input, but rather for a epoch, a bunch of epochs. So let's say we do it 100 times. What it means is that we go through each of this step 100 times, and on the same data set, by the way. So it do this again and again and again. So going through one pass is not gonna train your model. So we have to do it a lot of time. It's either tens or 100, sometimes more. So that's how we do it. So we have 1 minute. Let's speed run this real quick. We just did the whole thing. I hope you understand. So I put the same thing in for loop. The loss is this. This is the loss value. What we can do is keep track of the loss. So this is what we can do is create a variable called losses. Let me know if you have to go right now. We append it. So each epoch we're gonna put the loss in the array and see what it's look like, right? Before that, let's initialize everything again, run it again. And this time, I'm gonna do this. matplotlib.plot losses. And you can see it's going down. And it's going wrinkly. And we don't usually look at the training loss. What we have here is called a training loss. You train on the input and the target of that input, and that is for the training sets. And what we usually do is we split it into training and testing, just like what we did last time. You train it here, you graph the loss, but also you do the testing on the same thing without the backward and step. So you calculate the same thing by calling the loss function on a different sets of input and target and see what it look like. And we might encounter something called overfitting, where your training loss going down, but your testing loss or validation loss go up. So it go down for a certain amount, and then at some point it start going back up. That is when we know it is overfitting, because your model start to memorize the data set, or it start to learn only the training loss. It doesn't understand anything else. It's not generalized, you know. So that is that. I think I'm done. I'm so done right now. Any question, comment, concern? Please let me know.
I still don't have questions because like I'm trying to process everything.
Yeah. Take
But
time.
pretty soon though. Yeah.
Okay. Oh man, we went through too many things in my opinion. I hope I'm not make everyone even more confused about this. What I obviously is gonna be. It's a lot of stuff. What do you guys think?
I think it was really nice, detailed, and we have a recording so we can rewatch and
Okay,
make sure everything's clear.
that's awesome. I might have to edit the recording though, if you want to put it in the club. We can put it in the club,
Sure,
right?
I just need to rewatch it by myself.
Okay, yeah. Okay. That's it, guys. Any question, thoughts? Nothing's at all.
This is recorded, right? Or
Yeah,
no?
it is recorded.
Oh, okay. Nice. I think I gotta review everything again.
No,
just to
that
be,
you don't have to go through this, the whole thing. The recording itself might be even more confusing. What I would
yeah,
suggest
yeah.
is try to go through a data set, and I'll put this notebook, even though it's disgusting right now, it doesn't make sense. Try to run everything yourself, run a bunch of things, look for a different data set and see what you want and try to write a code for it. That way you realize you know the question exactly what you want to ask, and I think that might help. But yeah, that's PyTorch. I didn't even plan that we go through this. I think Andrew gonna go through it, but we just went through it anyway. That's it. Thank you guys.
All right, all right. Nice. Thank you, Montre.
Thank you. Thank you.